Hello student, we have started transition in inner transition metals, and in that we have started the D block element, that is the transition elements. We have already discussed what are D block element, their position of the D block element in modern periodic table, which is the most important question in board exam, and of course the electronic configuration of 3D series. Also we have explained the anomalous configuration of chromium and copper. We also deal with the melting point and boiling point of D block element, the density of D block element, why it is increases across a period, we have seen this, and also the atomic radii of the D block element, which kind of a trend is observed over there. The 3D series element, in 3D series element the atomic radii decreases from left to right, we have seen this. And now we are going to start part 2, and in that we have discussing variable oxidation states of D block element. This is the most important question in this topic. The characteristic property of D block element is their ability to exhibit a variety of oxidation state in their compound. What is oxidation state? It is the numerical charge developed on the element when it is present in the compound. Compound form करत असताना एखादा element जी plus or minus oxidation state achieve करतो ती आपल्याला इथे बघायची आहे. In case of D block element, we have seen that the oxidation states are variables. So many kind of oxidation state are found for one element here. Loss of 3d and 4s electron progressively leads to formation of ions. This is due to the fact that for bonding, in addition to ns electron, the D block element can use the inner n minus d electron as well. This is because there is a very small difference in the energies of 3d and 4s orbitals. Thus, depending upon the number of d electron involved in bonding, different oxidation state arises. The lowest oxidation state +1 is shown by Cr and Cu. Chromium and copper shows the lowest oxidation state, that is +1, and the highest oxidation state shown is +7, which is shown by Mn. An examination of the common oxidation state given above reveals the following points. Except for scandium, the most common oxidation state for all the rest of 3D element is +2, which arises from loss of 2 4s electron. This means that after scandium, d orbital become more stable than s orbital. Here, the rare oxidation state are given in parenthesis. Compounds having oxidation state +2 and +3 of these elements have ionic bonds, whereas bonds are essentially covalent in case of the higher oxidation state, that is from +4, +5, +6 and +7 we see the covalent bonding. Transition metals in higher oxidation state are strong oxidizing agent. Here is the table we can look over. The different oxidation state of element of the first transition series are given below. We know the 10 elements: Sc, scandium, titanium, vanadium, chromium, manganese, Fe, iron, cobalt, nickel, copper and zinc. We show only the lowest oxidation state +1 for Cr and Cu. For all the compound will show the +2 oxidation state, except zinc all the element shows +3 oxidation state. From titanium to nickel we see the +4 oxidation state, and from vanadium to Fe we see the +5 oxidation state, and chromium Mn Fe will show +6 oxidation state, and only the Mn shows the highest oxidation state, that is +7. Now let us discuss the ionization enthalpy of D block element. Transition element shows ionization enthalpy values that lies between S block and P block element values. They have high ionization potential values than S block and low ionization potential value than P block element. The first ionization potential values increases with increase in atomic number in a given series. The first IP values increases with increase in atomic number in a given series. The most important point is this. Now, the fourth one, the IP values can be used to predict the thermodynamic stability of their compounds. Smaller the value of IP of the transition element, stability of compound is greater. So, this is a reciprocal relation. Please mind well. Now, for the elements Sc, Ti, V, Cr, Mn, Fe, Co, Ni, Cu and zinc, the first IP values respectively are 632, 659, 650, 652, 717, 762, 758, 736 for nickel, 744 for copper and 906 for zinc. We see the trends in first ionization enthalpies of D block element in the concerning figure over here, which is plot against the transition metal and the first IP values. The atoms of element of third transition series possesses filled 4f orbital also. 4f orbital show poor shielding effect on account of their peculiar diffused shape. As a result, the valence electron experience greater nuclear attraction. A greater amount of energy is required to ionize the elements of third transition series. The ionization enthalpies of the elements of third transition series are therefore much higher than the first and second series. You can see this in the figure also. Now let us discuss the magnetic properties of transition elements. This is again one more important question which is asked in the form of short note or may ask in the form of problem. Transition element shows magnetic property due to presence of unpaired electron. There is a strong correlation between the magnetic behavior, electronic configuration and oxidation state. Paramagnetism arises due to presence of unpaired electron. Since transition metal ions generally contain unpaired electron, a large number of transition metal ions exhibit paramagnetic behavior. Magnetic moment mu of paramagnetic material can be calculated in Bm. Bm means Bohr magneton by using the expression mu is equal to n into bracket n plus 2 Bm, where n is what? N is the number of unpaired electron. A single unpaired electron, if it is present, it has a magnetic moment mu is equal to 1.73 Bm. We have calculated this. For example, if we take the example of Ni plus 2 ion, it has two unpaired electrons, that is N is equal to 2. The magnetic moment can be calculated as mu is equal to 2 in bracket 2 plus 2, that equals to 2.83 Bm. Compounds containing Si plus 3, Ti plus 4, V plus 5, Cr plus 6, Mn plus 7 and Cu plus ion. These ions are diamagnetic. Since these ions do not contain any unpaired electron, all electrons are paired, so these are diamagnetic in nature. Among transition metal, Fe, Co, Ni are ferromagnetic. When magnetic field is applied externally, all the unpaired electron present there in this metal and their compound align in the direction of the applied magnetic field, and due to this the magnetic susceptibility is enhanced, magnetic susceptibility increased. These metals therefore shows permanent magnetic moment and are considered as an ferromagnetic. Now how the problem is asked over here. See, calculate the spin only magnetic moment of divalent cation of the transition metal with atomic number 25. Firstly, you have to write the block diagram for this atomic number 25 metal. Solution is given here. For element with atomic number 25, the electronic configuration of its divalent cation will be Ar. In 3D we see the 5 electrons. See the figure. And in 4s 0 electrons are there. So 5 unpaired electrons are there. So n is equal to what? It is 5. So now taking formula mu is equal to n into n plus 2. that will becomes a under root of 5 into 5 plus 2, which is equal to 5.92 bm. So this is how we can calculate the spin only magnetic moment of divalent cation of transition metal.